Hello everyone, and welcome back. Today we're going to tackle a fascinating problem at the cutting edge of astrophysics, calculating the immense power output from an accretion disk around a black hole. This isn't just an abstract exercise. Understanding these processes helps us comprehend some of the most energetic phenomena in the universe, like quasars. Let's dive into our problem. We're considering an accretion disk around a black hole, and we're told it radiates 10% of the rest mass energy of the infalling matter. Furthermore, 10 to the power of 18 kilograms of matter is accreted every second. Our goal is to calculate the power output in watts. First, let's conceptualize what's happening. Imagine a diagram. At the center is a massive black hole, about 10 times the mass of our sun. Surrounding it, forming a flat spiral, is the accretion disk, a swirling structure of gas and dust. As matter within this disk slowly spirals inwards, friction and magnetic fields heat it to extreme temperatures, causing it to emit vast amounts of radiation. Now, let's identify our key variables and constants. The accretion rate, denoted as dm divided dt, which is the mass flowing into the black hole per unit time. Its value is given as 10 to the power of 18 kilograms per second. The efficiency of energy conversion, epsilon. This tells us what fraction of the rest mass energy is actually radiated away. It's given as 10%, which we write as 0.10. And finally, the universal constant, the speed of light in a vacuum, c. Its approximate value is 3 times 10 to the 8 meters per second. The fundamental principle we'll use is Albert Einstein's famous mass-energy equivalence, E equals mc squared. This equation tells us that mass and energy are interchangeable. A small amount of mass can be converted into a tremendous amount of energy. When we talk about power, we're talking about energy released per unit time. So the power output, P, is essentially the rate at which energy is generated. Combining these ideas, the power output from the accretion disk can be calculated as the efficiency epsilon multiplied by the mass accretion rate, dm, divided dt, multiplied by the speed of light squared, c squared. So P is equal to epsilon divided dt divided c squared. Let's substitute our values into this equation. P equals 0.10 times 10 to the 18 kilograms per second times 3 times 10 to the 8 meters per second. First, square the speed of light. 3 times 10 to the 8 squared is equal to 9 times 10 to the 16. So P equals 0.10 times 10 to the 18 times 9 times 10 to the 16. P equals 0.9 times 10 to the 18 plus 16. P equals 0.9 times 10 to the 34 watts. We can write this more formally as 9 times 10 to the 33 watts. To check our answer, let's consider the scale. The total power output of our sun is about 3.8 times 10 to the 26 watts. Our calculated power output for the black hole accretion disk is 9 times 10 to the 33 watts. This means the accretion disk is about 10 million times more luminous than our entire sun. This enormous power output is entirely consistent with observations of extremely bright astrophysical objects like quasars, which are powered by exactly this process in the centers of galaxies. The black hole's mass provides the deep gravitational well that allows this energy conversion to happen, but its specific value wasn't directly needed in this calculation because the efficiency was already given. In conclusion, we found that the power output of this accretion disk is an astonishing 9 times 10 to the 33 watts. This problem beautifully illustrates the immense power that can be generated when even a small fraction of infalling matter is converted into energy in the extreme gravitational environment of a black hole. It highlights why accretion disks are central to understanding high-energy astrophysics and the luminosity of active galactic nuclei. Thank you for joining me today. If you found this explanation helpful, please hit the like button, subscribe for more physics content, and share with your friends. Your comments and questions are always welcome below. And remember, if you have a specific problem you'd like to see solved in a future video, consider donating to the channel. We select a few problems each month for dedicated explanations just like this. See you next time.